So this is a discussion session where we are going to talk about open problems and open directions. And Seth, Seth and Mike Freedman
and Pavel.
And Pavel.
Yeah.
To lead this discussion.
Yeah. So it maybe a little too special because I can't say we're the most organized in the world, but we, at Arthur's request, we are not going to put the questions up on the whiteboard, though we will have a whiteboard for questions from the audience. I've gone around and asked a bunch of people if the questions are, or yes, and so I put up. Not everybody was forthcoming. I don't understand why people don't have more open questions, but I'm going to put up a few of them here, and then let's see. Okay, great. So sorry, and then I'm going to talk. We'll talk for about maybe 15 minutes. We have 45 minutes, I think. So we'd like to have the discussion happen while these questions are put up, and then I think we want to leave room at the end for people to suggest their own open questions. These are Pavel's, and but I'll talk for a little bit about questions that people gave me and questions that I have, and then we can chat about that. Pavel then has, you may note that he's got 31 pages of open problems in tensor categories. So Pavel's going to do as much as he thinks reasonable. The 31 clicks. And we'll take it from there. And it would be nice to have this be a real discussion section so that I encourage people to raise questions while we're talking. And maybe we can actually bring the whiteboard in a place where we can write questions up as we let me focus. I can't walk and chew gum at the same time. Okay. So here's some questions. I just listed the people asked them. Here's a good one from before.
Seth, as long as you're out of the room, as long as everybody's out of the room by 5, it's okay.
Okay, good. We'll be out by then. Our plan is to finish before by the time this is over, we'll all need a glass of wine. Let's put it that way. So I asked Peter, do you have any open questions? He said, besides the obvious? And I said, what's the obvious question? He says, are there any more good quantum algorithms? We've got Shor's algorithm, we've got quantum simulation. We've got a whole bunch of algorithms for linear algebra, like quantum singular value transform. You can then take those and apply them to problems, and for instance, in algebraic topology, like simplicial homology and persistent homology. But are there more good quantum algorithms? Can we solve shortest vector on a lattice? It's a good question. Actually, let's take a little vote. This will be fun. How many people think that there's some really super awesome quantum algorithm out there just waiting to be discovered? And if we keep working, we're going to do it. Okay. How many people think there isn't? That's it. Oh, nobody's willing to step up and be contrarian. How many people have no idea? Okay, great. It's a net positive. So then I talked with Eddie, and Eddie said, let's see if we can get here. Why don't people work to develop new quantum algorithms? And I and other people are doing that. But it is actually true that there's, even though people are trying, there's kind of a dearth of people working on algorithms. That's why I think this conference, which is such a lovely conference, and I know you're out there somewhere, Arthur. I know you're out there somewhere. But it is a great way to explore these interplays between different aspects of mathematics and quantum information for us, and also just quantum mechanics in general. Because I sense that, things like algebraic topology or algebraic geometry, where there's a lot of linear algebra involved, well, quantum computers are exponentially better and things like that. No. Yeah, good, yeah. And I were talking about that just the other day.
Repeat the comment. We couldn't hear it.
How many people expect it to work? Okay, Good. So yeah, so this is, I think that there's a lot of space for working on this kind of question. But I don't know if the algorithms are there or not, but we can but try. Okay. Yeah. You can say anything you want. I'm going to go through some questions, and then there's going to be a general discussion session. What do you say something, Eddie? Yeah, he's got a microphone.
Yeah, I was just asking whether we were allowed to speak.
Yeah, speak.
I mean, I think there's another approach to the discovery of quantum algorithms.
Can you speak more directly into the mic?
Yes, excuse me. I should identify myself, Edward Farr. So I think that there is another approach to the discovery of quantum algorithms, which is take existing heuristic algorithms and analyze them. And, we have examples, for example, the quantum approximate optimization algorithm, which I'll speak about tomorrow, where we have provable worst case performance guarantees at low depth. And we can ask questions about these algorithms and try to answer them. So I think without necessarily constantly saying, are we beating the best classical algorithm? Because I think when you mean discover quantum algorithms, typically it's hidden in that. Can you find a quantum algorithm that provably outperforms the best classical? And so if you remove that, I think there's a lot more room for trying to explore the power of existing quantum algorithms.
Yeah, I think that's right. And you've done it. Yeah, it's worked well for you. Yeah, and I mean, just for instance, is Sasha Schmidhuber here? Is he still around? Yeah. So Sasha is a master's student. He's with Renata Renner. He's doing his master's degree with me here at MIT. So the master's degree is going to be, that's about 70 different ways of trying to find the Euler characteristic using quantum computer, because many of them are based on diagonalizing 2 to the n by 2 to the n matrices, which may be sparse, right? So maybe one of these is going to work. We don't expect it to work because even approximating the Euler characteristic to multiplicatively is sharp P hard, right? So, but heck, we're going to find stuff out along the way. We already are. Sorry, Sasha, I just thought I'd advertise your work. Okay, going forward here. This is from Michael Freedman. This is a very nice question. We know that almost all unitaries take time doubly exponential, 2 to the n over n qubits to implement. But can we exhibit a specific unitary that is hard to construct? If we take a random circuit of size 2 to the n with very high probability, that's going to be very hard to construct in any other way. But that's how can we do it specifically? We exhibit a specific unitary, and that would be really great. Michael, do you want to say a word or two about this? Yeah, can we get the?
I think this question is a nice analog of the problems about expander graphs that the Erdős approach was to build graphs with interesting combinatorial properties, so-called communication graphs, graphs with a small valence, but yet it was rather efficient to get between any nodes and a small number of hops. And for many years, because of the work of Erdős in the 50s, 60s, it was known that the generic randomly constructed graph had this property. But it wasn't until the number theorists, people like Peter Sarnak at Princeton, sunk their teeth into the problem that anyone had any idea how to explicitly construct a graph with these properties. And I think we see something similar here. We know if we build unitaries randomly, the construction will generically be irreducible. That it won't, there won't be a shortcut to the one you build. But still, you'd like to know how to build a hard one. And I think this question is particularly interesting in the differential geometric context. Many of you may know the work of Mike Nielsen, joined later by many collaborators, in which he put interesting metrics on the symmetry group, SUM, the symmetries of the Hilbert space. And they studied left invariant metrics on this Lie group. The invariant metric was supposed to reflect the relative difficulty of moving in different directions. In the Lie algebra, you can have 1 body, 2 body, 3 body, so on directions. And for instance, Brown and Susskind, for reasons to do with quantum gravity, studied metrics, have been studying metrics where it's exponentially more expensive to move in higher body directions. And then and that also, not just the quantum gravity application, but that's really reflects the engineering difficulty of making controllable multi-qubit interactions. So in both subjects, it's natural to consider these metrics where it's easier to move in small body directions. And you can, again, make volume and diameter analyses and show that most of the Lie group is hard to get to. But finding any particular place in the Lie group is no problem.
That's great. So does anybody know how to get my display back here? Mirror display? Where does it say here? Mirror. Just keep.
Seth, can I ask a question?
Okay, good. Yeah,
Um,
this is a very.
Seth, yes, Renato.
Yes,
Um,
yeah.
I have a question about that. Maybe it's a question to like Freedman. The classical version of that seems to be that given a random permutation, or maybe just even a random function, it can we prove, or in the set of all random functions, can we find one for which we can prove that it's hard to construct? And this is kind of a computer science problem, a classical computer science problem, which probably has been studied.
Yeah, they're
extremely extensively.
functions over n classical
Right,
bits.
yes,
And
yes.
you know, almost all of them are going to be very, very hard to construct.
Yes, but we don't know which one. We don't have a specific one. So my question is, would we expect the solution of this problem to be maybe even easier because it's a nice geometric problem, as you pointed out? I think
know
if
that
you-
almost all of them are,
Yes.
right? But we don't, yeah. Yeah.
yes.
There's no sound.
Can you, yeah, can you explain what do you mean by increment?
Could you give Mike the microphone?
Sorry, Arthur.
Yeah.
Okay, all these problems, to be stated precisely, there's a parameter involved, like the dimension of the Lie group, 2 to the n, or sorry, that's the dimension of the Hilbert space. The Lie group would be the square of that dimension, or the n in the permutation group. But said simply without the parameter in the statement, what we'd like to do is identify a unitary in a large SUN that's difficult to get to by following a geodesic in one of these weighted metrics. And I think the analogous question in the permutation group is a single permutation, or more technically, a family of permutations, which is a function of n, where the number of letters in the word that describes it has to grow rapidly with n. So in the case of the unitary group, I feel rather confident in saying that no such unitaries are known. This has to do with conversations with Michael Nielsen and Evan Brown, but I think it's not known. I don't know the literature on the symmetric group, so that's perhaps someone in the audience does.
Great. Yeah, that's a great discussion. Okay, let's move on. Let's see what we got next. Okay, this is from Xiaogang. Can we and how can we classify quantum field theories? Can we define quantum field theories as the low energy limit of lattice qubit models? You want to say something about that, Xiaogang? Can we have a microphone down here for Xiaogang?
Yeah, the question really is that we know there's a quantum field theory supposed to describe our world, and it's very important. And but the question is that in general, what is quantum field theory? Can we classify different quantum field theory? You know, there's a constructive quantum field theory. Try to put the quantum field theory in a firmer ground. You know, Arthur have made a great contribution there. But in general, whether this is can we have a general theory of all quantum field theory? And in condensed matter physics, that means that can we have a general theory of all the gapless states, all the critical point because that's supposed to describe by quantum field theory. So this really relate to this the general understanding of a quantum critical point. And we heard today is a talk about the Van Neumann algebra, and which may be related. And but I don't know what really is a quantum field theory. So there's a very conservative definition. That is this so-called low energy limit or some kind of gapless states of some lattice model. This is a very, very conservative definition. And but I don't know whether this definition would give rise to some kind of I don't know. I'm not familiar with this Van Neumann algebra, but whether a certain kind of Van Neumann algebra corresponds to these lattice gapless states. And then if that's the case, then whether some other more general Van Neumann algebra correspond to what? Maybe boundary of some one higher dimensional lattice state or something more weird. So this is kind of question associated with the gapless states, some general understanding of gapless states.
Thank you, Shogun. Actually, Shogun's question is just a rewording, another way of looking at a question that that we didn't have time to write down. So another way of asking a very similar question is there any way of using physics, and you might want to put a modifier there, saying conventional physics or physics that we might technologically access in the next 100 years, or you might want to put some modifier in there. But is there any way of using physics to create an implementable computational class which is stronger than BQP? Because if it's really true that field theories describe, what can be done in the lab or what happens out in the world, and if it's also true that lattice models converge well and give the solutions to these field theoretic questions, then there's a strong indication that they're in BQP. There are papers by Preskill and Jordan, for instance, which actually carried this out for 5-4 theory. And I think there's an ongoing program to do it for gauge theory. But many physicists have asked me whether perhaps physics of critical systems near a critical point, conformal field theories, might, if we could probe them adequately in the lab, set up initial conditions and make measurements, produce conclusions, even with the errors in there, that would be stronger than BQP. And then some other group of physicists who are even more abstract say, well, what about field theories that don't even have a Lagrangian? They talk about this 6-dimensional theory that's supposed to be in the background of everything, according to Witten. So is that computationally beyond BQP? And the reason I wanted to cut this off with some practicality horizon is we all know in computational theory, if your model is, this is the beauty of physics, it knows more than mathematics. Physics tells you when you're talking crazy, because it tells you you're doing something dumb if you say, okay, I'm going to make a computer out of billiard balls, but they're going to reflect perfectly. There's so many easy models in computation, which are sharp P complete, but the models are ridiculous because they're allow like exact multiplication of real numbers or exact reflection of billiard balls. So I just want to confine our thinking to physically, potentially realistic models and just ask whether, it's really two worlds, classical and quantum, church theory, quantum church theory, or maybe in our lifetimes of the younger people in the audience, we'll see a third model, which is even stronger.
Yeah, that's a great question. I mean, when David Deutsch, his original paper, his main goal was to find a quantum church Turing hypothesis, and he said he hypothesized that any quantum system could be simulated exactly by a quantum computer. That's how he stated it, which I think that's probably a little harsh, but we know that it's quantum systems that have local interactions and a finite number of local states, those appear to be simulatable on a quantum computer, and so would fall in BQP. So, but of course, they're in quantum field theories with infinite number of degrees of freedom, and also in questions that involve gravitation, where frankly we don't know what happens inside a black hole. It might actually be that there's something more there.
So the question of, there's computational power hidden in type 3 factors, right? That's something we want to get to the bottom of.
Hey, so this is, what is the entropy dimension of large matrix algebra? Yeah, you should say what you're asking. I'm not gonna get it right.
Yeah, no, I mean, yeah, so I have to do this blackboard. I'm a mathematician. I can't just do this otherwise, right? So the question is that there exists a constant that for all n, there exist two unitaries, u1, u2. So that if I calculate the relative entropy of the state with respect to 1 over n, right, the maximum state, this is less than a constant relative entropy of the state. Sigma, where sigma is u1 permits, plus, so there's a big bracket, the infinite over a sigma 2 to the relative entropy of rho. Okay, so this is the mathematical question. So I want to find two unitaries so that if I control the relative entropy, A is the first one. I control the relative entropy and relative entropy. Relative entropy because it's a little bit stronger than factor gamma. So why do I think this is? Well, if I have these unitaries, eventually we get maximum. Which generate the you find two maximum units. Just one algebra formulation. Of the large algebra. So there is an x and a y direction, and these together to the whole algebra and we can have it.
What's the matter? What's the matter with e to the minus I rho and e to the minus I sigma? Won't they? They'll do that, won't they?
So whether that's n or 2 to the n doesn't matter, right? I mean, if it's independent of dimension, 2 to the n, 2 to y would also work. There is work of Joanna which proves a similar inequality for where a similar inequality, which would probably imply that if your dimension of the Hilbert space is 2 to the n, you can probably do this with constant n. But I wanted with constant with a universal constant, right? So, I mean, this would be unitaries which are probably not easy to compute. Because if you had them, you know, if you have computable one and or coming from small circuits, you just have to iterate them a certain number of times, because this essentially means you're iterating this only a finite number of times, and voila, you're done, right? So for instance, if you formulate that for unitary representations and extend this a little bit, you would have two unitaries which can calculate the irreducible part of SU2 by an algorithm, right? So if you have similar inequalities, this would give you a very fast algorithm which calculates all the reducible pieces of an arbitrary state. I don't think that's reasonable to expect. So what I'm saying is, instead of answering your question with one unitary, ask for two, and one of them can be easy, but the other one won't. Yeah. So it's just that because, you know, if you calculate the commutator of the relative entropy for things which commute, they are diagonal with respect to the spectrum of the one. So the one is not enough. That doesn't work, right? So this is not good enough. But two should be enough. And the question is, you know, maybe you're three. I mean, I'm also happy except 3, 4, 5, 6, but I want a finite number and I don't know what that number is. And I want to have a very strong spectral gap. If you formulate it like this, the mathematical formulation is not so relevant, right? Very strong gap to gap, right? So somehow an expander with two elements. And so yes, there are expanders with two elements, and there's a result by Joanna which somehow does quantum expanders with two elements, which comes extremely close to this inequality.
Could you just say how rho is quantified?
Oh, this is a state on the Hilbert space.
But exists or for all?
No, this is of course for all, right? For all rho, the relative entropy will be reduced by knowing the relative entropy for. Oh no, that's not my phone. Okay,
Sorry.
Yes, just want to know whether they exist. Yes. I mean, yes, you're right. So you can say there is an example for this to work. Take what we call the Freedman factor, which is the limit of random unitaries, and then this estimate. At least the spectral gap is okay. I think even for the free group factor in infinite dimension, this estimate is unknown. I mean, we are talking open problems, right? So this strong estimate, even for the free group factor, if I'm not mistaken, is already unknown.
So maybe you can
But
use.
we hope that's true, right?
Maybe you can use probabilistic method to show, which means to show that the probability that such
I wrote two
exists
papers.
is positive.
I read 2 papers in this direction using free probability, and I'm not able to do it. I mean, that doesn't say a thing, but it's not that I didn't try, okay? I mean, we're talking open problems, not, yeah, I mean, I agree. This is for that particular choice, but it would only do this in the free group factor, which is very special. And it wouldn't tell you something about, you know, a concrete finite dimensional unitaries, right? Anyway, so here we go.
Good. So I suggest that I have a bunch of questions that I think the rest of these are just questions that I was going to ask, but Pavel, let's turn it over for you right here. These are very obvious questions. So why don't you come up and talk about this? Here, these are just obvious questions. Are there useful near-term applications of quantum computers beyond quantum simulation? Can we do something now that would be useful? What are potentially useful applications for quantum networks, distributed sensing, or game theory? How do we get fault tolerance? Get the fault tolerance, get real noise and technological constraints. We have nice theorems about it, but are we actually going to get there? That's going to be tough. I was very heartened by Misha's talk and knowing that Q era now has some nice fault tolerant results. Can we construct a full self-consistent theory of quantum gravity based on quantum information? Beats me. I don't know. So and that there's one thing quantum machine learning. There's one thing before Pavel goes up that absolutely must be talked about. Can quantum mechanics and quantum information add to our understanding of pure mathematics and vice versa? And the answer is yes. Thank you, Arthur, for organizing this wonderful conference. I want everybody to say one count of 3. We love you, Arthur. 1, 2, 3. We love you, Arthur.
Thank you.
Full screen.
Okay, thank you. So this so maybe I should say a couple of words. So Victor and I are co-authors in many papers, and we will present some open problems in tensor categories that we've been thinking about for many years. Some of them many years, some of them not so many. But these problems are much more down to earth than the ones we have discussed before. So they are very concrete. Yet, some of them are quite difficult. Others are, I think, doable. So Victor is going to explain.
I hope that some of these problems are solvable. So the first problem, or maybe type of problems, we want to study fusion categories and the small number of simple objects. And well, basic problem is to decide whether there are just finitely many of fusion categories with any fixed number of simple objects. So physically, simple objects are particles in your system or something like that. I don't know. Something is known about this problem, but definitely, so what are interesting results? So really, you can do something up to rank 3 or a little bit more. So in rank 4, when you have non-self-dual objects, Hannah Larson did something. In case when you have symmetry in your categories, the symmetric category, this is kind of something very classical and follows from classical. So problem is to study finite groups where you have only finitely given number of conjugacy classes. And this is something classical due to Landau. For modular categories, there is great work by 4 authors, and John Hahn is here. So it was generalized related to braided fusion categories, and again, some authors are here. So that's some known results. Well, and it's a difficult problem, but you can try to approach it. Try to come up with some other problems which give you close to this problem. So, for example, one possible way to do it is to try to find an upper bound for rank of the infinite center of your fusion category in terms of rank of original category. And there are some results by Pavel about this, but I still don't know. It would be interesting.
So the problem is that the bound for groups is exponential. If you have such a bound, you can derive rank finiteness. But the problem is that even for quantum doubles of finite groups, this bound is exponential in the rank of the original category. And in fact, it has to be exponential. It's at least exponential of cube root of n. So this shows that the bound will be big and then therefore not so easy to prove.
One more class of problems is to do something in positive characteristic. And this might sound strange for physics people here. But we do believe that kind of understanding of positive characteristic is helpful to understanding things about characteristic 0, and in particular about real physical problems, or at least categories related to physical problems. And in this case, we don't even know that kind of that final answer is finite, but you can try it. So it's possible that these categories have some deformations. Kind of, we know that it does not happen in characteristic 0, but we can't prove it. And you can
maybe I should make a comment that why characteristic P is useful, because the general principle is that in characteristic P things become more commutative. So, for example, even quantum mechanics in characteristic P is closer to classical mechanics. So reducing modular prime is a way to take classical limit and yet remain in the quantum world. And this has been used many times to solve problems about quantum theory. In categories also, braided categories tend to become symmetric when you reduce modular prime. This is what happens also in a lot of problems. And so symmetric categories are easier to understand because they're related to classical symmetry. So this is a principle that we practice all the time. No, it means that it's a modular arithmetics. When we work modular 2 or modular 3 or modular 5, not over with complex numbers, but with numbers modular.
I mean, you replace complex number by some other field.
Yeah, field of characteristic field, which is an extension of finite field.
Okay, thank you.
Is that clear that braiding becomes trivial?
Not always, but for categories arising from, let's say, quantum group at the root of unity, if the root of unity is of order P or 2P, where P is a prime, then it does become trivial. And they become symmetric, that's then we can understand them much better in some sense.
Okay, so here a few
Yeah,
more
maybe,
problems
maybe
about
some
positive.
additional. Usually in physics, we say we're only interested in category based on complex number C. You know why we're interested in this other characteristics? Whether there's some reason to say this may, yeah. So I don't know whether.
So they have lifts. Some of these categories have lifts to characteristic zero, which means that you can replace finite field by p-adic field, but this is as good as have complex field, because algebraic closure of p-adic field is actually isomorphic to the complex field.
One answer to Wen's question is mathematicians have had a lot of success warming up on characteristic P to do a harder problem. Like an analog of the Riemann hypothesis was proved over characteristic P.
Yes, and in fact, Langland's fundamental lemma was proved in the following way: that you first prove a statement with characteristic P, which can be done using algebraic geometry, and then you use some logic or model theory to prove statement in for number fields, which is actually of interest in number theory.
More comments? Well, let's move on. So another interesting thing is to study so-called big group of, well, now it's modular tensor categories or something closely related to it. Some obvious categories of this type are Greenfield centers. So kind of, for example, things that we built out of Levin-Venn model, the Greenfield centers, but there are some others which are not. And you can study difference between these two things by introducing some particular group which controls this. And elements of this group, they kind of contain each this kind of class of equivalents of various modular categories, and there is one particular representative of this class, which is smallest one, which is called complete anisotropic. And it would be great to classify them, but it's probably baby version of this problem to classify of quantum field series or something like this. So, and because of this, I think it's very difficult, but very interesting. So even partial progress would be great. And just kind of maybe to be a little bit more concrete, so recent and great result is that if you look at some specific categories associated with orthogonal group, they are all of order 2 in this fit group, and it's known that there are kind of infinitely many linearly independent things of order 2, so kind of they're linearly independent of a field with 2 elements. But we don't know about kind of separate elements. So most likely each of these categories it represents non-zero element in with group, and kind of all of them are linearly independent, but it's not known. So it's kind of more concrete problem of this type. Yep.
I just want to make a comment for the physicists here. So this weight group is very mathematical. It's modular tensor category for any models or modular order quantum level. And there's a kind of, I don't know, read it down anyway, there's a conjecture that this weight group has a map go to 3-dimensional non-trivial QCA. So for those who are familiar with the QCA, so those are the more interesting. The word QCA is kind of really a straight name. It's just locality preserving automorphism of local algebras. And it's very difficult to find non-trivial ones. The only one right now, mathematics, a candidate with 3-dimension, which means modular quantum circuit, which is given by the 3 fermion made into a QCA. And there's a conjecture you can go from weight group to all non-trivial QCA. In particular, the Fibonacci theory will give you the first possible infinite order QCA, non-trivial.
Can you tell for me what is QCA? I mean, what
QCA supposed to mean quantum cellular automata, but the modern term means locality preserving unitaries of a local algebra.
Thank you.
Yeah, maybe I should add that just last week I heard a lecture about some work of Greg Moore and his collaborator, where they were interested in conformal field theory, which have time reversal symmetry, and then they showed that this is equivalent
considering modular categories, which are have order 2 in the width group. So they were interested in classifying such categories for that reason. And this is related to this problem.
Maybe let me also add that my understanding that this width group classification corresponds to the gapless boundary for topological order. I mean, the topological order which cannot be gapped. Yeah, and
That's right.
so exactly. So this is really interesting. And how many of them just how to classify them? Yeah.
Yeah. Well, we have so you can define this with groups of symmetric categories for group of super vector spaces. What's kind of studied a little bit, but you can do more general groups. And well, I think it's interesting,
especially in positive characteristics.
Yes, it's actually seems to be interesting question to just to give kind of relevant definitions for non-semi-simple setup. And actually, it's even more interesting that we don't know any potential candidates for non-trivial, non-semi-simple, I mean, non-trivial elements which are non-semi-simple and which cannot be represented by something semi-simple. And this is a little bit strange. And actually, if you do things in positive characteristics, you're just forced to deal with non-semi-simple categories just because the infinite centers of something semi-simple, it might be non-semi-simple. So you need to develop it just to start talking about positive characteristics. So it's kind of some other aspects here. Okay, we move on. So this is about symmetric tensor categories, maybe over complex numbers, but which are a little bit non-classical. So many examples were initially defined by Deligne, and sometimes they're called Deligne's categories. Well, there are many questions. I mean, maybe main question, but don't really understand them structurally. I mean, to have any kind of idea how a structure here might look like would be great, but at this moment it's too open that we did not even try to ask this. But some particular questions are, well, this is problem which does not allow me to sleep well. So in characteristic 0, there are plenty of examples of. I'm sorry, not this one, another one. But we want to study so-called incompressible tensor categories, and this means that you cannot come up with a functor from this category to something smaller. And in characteristic 0, 2 known examples: category of vector spaces and super vector spaces. So kind of physically, you have bosons and fermions and nothing else. Well, for these categories which grow very fast. We don't know whether this, I mean, what is the case, and we expect that there is nothing else, but it's not proved yet. Maybe something else. So there are very, very recent examples of this type due to Nate Harman and Andrew Snowden, and well, we don't understand them at all, and it would be great to understand them.
But they have discovered a new construction that provides completely new tensor categories, which we didn't know before. But those categories are very, very large.
And yeah, and at this moment,
they are not. They don't come from any kind of group Hopf algebras. They are really super exponential growth, but of new kind that we haven't seen before.
Yeah.
You just take an object and you raise it to nth power. And then you look at the length of that. So if for group theory, group representation grows exponentially, but there are categories where it grows super exponentially, like Deligne's interpolations, which, by the way, have been used in statistical models by Richkov, for example, and others.
Yeah, and we want more examples. So we don't understand structure series, so maybe to get more examples would help, or maybe not. So. And quantum subgroups. So this is a study of this Bezzumina-Witten models. We heard about this from Benzel today, and maybe from other people. And you want to study module categories of them, just all of them. Well, maybe 5 years ago, it was not so much known about this. So kind of case of A1 type, so say parameterized by kind of Lie theory. And case of A1, A2, A3 was more or less known, but it was very difficult. But recently we had a great progress due to several people. Kind of much more is known now, but I want even more so. Well, for type A, many things are known, but I don't think that all of them. But maybe Terry will tell me that I'm not level. I'm not up to date. But at least to some quite high rank, many answers are known. It would be great to have type A completely or something. that would be absolutely fantastic. So maybe another thing. So we have new methods which kind of work in this setup. They kind of work for categories which kind of come from roots of unity divisible by something. I mean, by numbers like 2 or 3. But there are some other roots of unity, and there are some very similar but little bit different categories. It would be interesting to see how it works in this case. These categories, they make sense in positive characteristic, and kind of question about model categories make sense in positive characteristic. But I think methods are not kind of directly generalizable, and it would be great to see what happens. I think answer is definitely different. So there are more things in positive characteristics than for quantum roots of unity. But how many more? I don't know. And that's it. I think that's it.
Well, yeah, I mean, famous.
So it's just a selection of problems. It's not all possible.
No, I mean, so for example, if you want a problem about high group, I can give. So we have braid group. So let's take the quantum double or Greenfield center of high group. So there is a braiding. So we have braid group representations. Now, if you so there is a question about. So there is a question whether high group comes from some conformal field theory, or so the examples that come from conformal field theory that we know, they come with the conformal blocks are hypergeometric functions of some sort, and so therefore monodromy representations are what Delin calls motivic, which means they come from hypergeometric functions. And so the question is, suppose we take high group representations, the simplest ones, are they going to be motivic? Do they come from hypergeometric functions? If, of course, if they don't, it is really hard to prove. But of course, if we knew that they don't come, well, this means that they definitely, it doesn't come from the family of conformal field theory that we know it.
So, Pavel, after that beautiful set of questions, maybe it would be nice to see if there's some young people in the audience who have questions.
Yes, absolutely.
Yeah, that's great. So let's we can put them up on the board. Arthur asks for young people in the audience who have questions, and I think this also can apply to people who just feel young as well. Yes, Arthur. I have to say, Arthur was my undergraduate advisor in physics at Harvard, and it's remarkable that he looks now exactly as he looked 40 years ago. It's kind of crazy. I don't know how he does it. Actually, let's do that. Arthur, do you have a question?
Oh,
Arthur?
I have so many questions, but not now.
Okay. All right. So come on, be brave, step up. Yes.
All right. That's Dave Pennies. Just in the spirit of Pavel and Victor's questions and Mike saying something about Hogger up, in the spirit of that is, can you construct infinitely many near group fusion categories of type G plus size of G? So what does that mean? It means that I've got fusion categories where I have a group's worth of invertible objects and then one other object, And when I square it, I get all of the group elements. And that number, call it n copies of itself as well. So if you can do this for, say, just for Z mod P, for some prime P, for all P, that would just be a tremendous, absolutely tremendous result. N is the size of the group.
Hey, good. Yes, that was great. I'm not going to write it on the board because I wouldn't get it right.
Well, maybe Dave, you should go up and write it.
Go ahead and ask next question. I think it's okay. We don't, we need,
Yeah.
in keeping with Arthur, on time. Go ahead and ask.
Hi, I'm Steve Flamian. There's a long-standing question about the existence of a self-correcting quantum memory. And this even needs some, I think it's not adequately formalized mathematically yet, but an analogy with the 2D Izing model. So let's contrast the 1D versus the 2D Izing model. The ground states store 1 bit of classical information in the all spin down state or the all spin up state in both cases. But the 1D Izing model is not thermally stable at any positive temperature. The order is destroyed because I can create a domain wall and propagate it across the system with a constant energy. So at any positive temperature, you destroy the order and you leave the stable phase. You can't keep the information encoded, classical bit encoded for a very long time. Let's say exponential in the system size, the number of spins. So the question is, can we find a quantum analog of the 2D Izing model? So by contrast, in the 2D Izing model, there's this Pyrrol's argument that says that, to create a domain wall, you have to grow some puddle of spins, and there's an energy penalty, which is proportional to the length of the boundary of that. And so this is going to get suppressed. The probability of creating a large puddle is suppressed by a Boltzmann factor, which is like E to the minus L at some constant temperature. And so at a sufficiently low temperature, and the entropy doesn't compete hard enough, so you get a stable phase. You can, at least with respect to thermal fluctuations, no on-site fields. The 2D Izing model is a stable classical memory in that it encodes a bit of information for some exponential time. So the quantum analog of this would be find a system, preferably in 3 dimensions or smaller, that has the property that it's stable, in the sense that just by growing the system size, I can put it in contact with a thermal reservoir. I prepare it in some initial state. I put it in contact with the thermal reservoir. And then for some exponential amount of time, I can read out the quantum state that I put into it. So I think this is a really fantastic open problem. Like I said, I don't think that it has even yet been adequately formalized mathematically what the sort of rules are.
But in 4 dimensions.
Yes, in 4 dimensions, we know that this is possible because you can basically take 2 copies of the toric code and take a product of them. And then both of these, it turns out that the excitations look very much like the 2D Izing model. You get little puddles that have the same Pyrrol's argument applied. So we know that this is possible in 4 dimensions. Is it possible in 3 dimensions or smaller?
I must say, together with Seth, we found very illuminating what you guys in mathematics world consider as down to earth question.
So in quantum machine learning, there's many examples of these things called barren plateaus. Basically means if you try to train some quantum neural network, it's going to take you an exponential amount of time to do it. And recently there's been more and more examples of why these things happen. So the question I've been thinking a lot about is, with so many causes of these barren plateaus, is there still hope that quantum machine learning is still going to be useful to learn something about physics?
If I may comment on that, so I think you're talking about a specific type of quantum machine learning, which are variational algorithms. Right. So there's plenty more to quantum machine learning than variational algorithms. There's lots of data analysis, algorithms that don't rely on variational quantum circuits at all. We're relying on things like, for instance, large scale matrix inversion and stuff like that. There's a question of how you get, my question that I put up is, if you're going to apply quantum computing to find some pattern in data, which in principle you could do by diagnosing some very, very large data matrix or covariance matrix, how do you get the classical information and the large amounts of classical information into an eensy quantum computer? You know, we don't actually have quantum random access memory yet. It would be hard to build. Can we do classical pre-processing somehow to get the data in a form the quantum computer can use? It's it's an open question.
It's related very nicely to the very first question that Peter asked about quantum.
Well, I have
useful quantum algebra.
I'm sorry, what I don't understand about barren plateaus is why don't they play classical machine learning in the same way? What's the difference?
Oh, I can, yeah, do you want to answer that? I know the answer.
What, the guy who asked?
Oh, this is I would like to recommend a paper by a student Bobat Kiani and Eric Curiel, who are graduate students at MIT. So in classical machine learning with very large neural networks, if the number of parameters in the neural network, the number of weights is much larger than the actual data set, which is often the case, then first of all, the network is trainable in the sense that you don't hit local minima because it's over parameterized. And then the gradients are actually because you're not stuck in this position in quantum information where the reason you have barren plateaus is because if you have two random states in a high dimensional Hilbert space, their overlap and their variance is roughly 1 over the dimension of the space. And so, you know, you're going to be stuck almost all the time with these barren plateaus. That simply just doesn't exist. That problem just doesn't exist in the classical one. Sometimes you do get vanishing gradients, but it's much less of a systematic problem than in quantum variational method.
Finding ways to parameterize your problem appropriately is a, in a systematic way could be actually an interesting potential solution.
Absolutely, and there's a lot of literature, but I haven't read all the literature now because it's expanded too much, but there are a variety of suggestions for, as Misha says, parameterizing your data in a way so that you don't necessarily get barren plateaus. Yes?
Yeah, I have another question on kind of the interaction between the physics and machine learning community. So I've been seeing more and more work on using, let's say, techniques from field theory, renormalization, Wick rotations, Feynman diagrams, etc., to build a theory of interpretable neural networks, etc. And I'd be interested whether people think that's a promising research direction on how physics can inform computer science.
No, that's a great question. I mean, this, of course, I'm going to say a little more about what Michael said. You know that Michael Freedman, that his whole question about can you have a quantum field theory that, for example, that might solve some problem that you can't solve on just an ordinary quantum computer. Michael was proposing back in the 1980s that because I'll get this slightly garbled this slightly, Michael, but it was amazing insight because zeros of in some topological quantum field theories, then you have determinants that are Jones polynomials, and determining that the zeros of the Jones polynomial is NP complete. So Michael said, hey, maybe these topological quantum field theories will just solve this problem for you. And am I getting this right, Michael? Oh, he had to leave, right? Sorry, he had an appointment in the math department, so he can't correct me. Yeah, but that would be very interesting. Yeah, and of course it's extremely apropos for this conference because the emphasis in the conference from the physics mathematics side has been aspects of quantum field theory. And it would be great to be able to apply such things, for example, to machine learning problems.
Last minute.
I have questions. It's for the fusion category. So for given fusion category, can we construct some cohomology ring, which is isomorphic to the fusion ring? So
Could you write your question down? I think, I didn't understand it. It was for you guys, right? Yeah. Did you understand it?
So suppose we have a given fusion ring, and can we construct some cohomology theory, such that the cohomology ring is isomorphic to that fusion ring?
You guys want to maybe start repeating the question?
So fusion ring may be non-commutative, so no, but I mean, there are
known to be quantum homology of Grassmannian, something like this. So there are some positive things in this direction, but definitely general question is wide open. I mean, we don't know what Grassmannian or higher up category should be.
I mean, it would have to be something like quantum cohomology, maybe variant cohomology, because ordinary cohomology usually is important.
Related to the question that for the given fusion ring, do we have a finite number for fusion category? Is this a no? Yes. Oh, that's a no. Oh, I see. Okay, thank you. Okay. Yeah.
I just have a question. This is oh, sorry.
Yeah, go ahead. So maybe it's a last question because.
Sure. My name is Gabriel Wong. I have a question related to the question of whether quantum gravity can be constructed from quantum information theory. So maybe a more basic question is there a reason why quantum information should be described by gauge theory? This is somewhat related to some work I'm doing right now on measurement-based quantum computation, formulated as a gauge theory. I think it's well known that topological quantum computation can be formulated as gauge theories because TQFTs are oftentimes like transcendence theory. I was very surprised that measurement-based quantum computation is also a gauge theory. And I think there's a sense in which the basic fact that quantum information is non-local, but we're local, so we want to probe some non-local degree of freedom as a local observer might force like a gauge theory upon you. And so I think if you can, I'm kind of curious because we have so many quantum information people here. I'm kind of curious if it is either understood or what people's opinions are about whether quantum information should be described by some kind of gauge theory.
I think that's an excellent question to discuss during the reception.
I think that's a great idea.
Yeah.
I think that we should take advantage of the fact that Arthur is here looming as above us like the great Wizard of Oz. And to thank him again and to thank the organizers of this conference, and particularly Crystal, who is right up there. Let's give them all a big round of applause.
I want to thank all the speakers today for a wonderful set of talks. And I look forward to the ones tomorrow and the next day and the next day. I think it's a great meeting.